The LabNow CD4 analyzer provides the ability to digitally image fluorescently labeled antigens for the express purpose of quantifying the viral load for an HIV patient. A critical aspect of the design of the CD4 analyzer was rooted in the optical system. The optical system design needed to provide quantifiable data for each biochip inserted into the unit and then subsequently imaged. The assay called for 2 fluorescently labeled antigens, each with different spectral characteristics. One of the antigens absorbed light in the green region of the visible spectrum, while the other absorbed further into the red. What is presented here is a simplified version of the spectral and optical analysis performed as part of the design effort needed in generating the technical requirements for the optical subsystem created by Sensivation and integrated into the instrument by my team while at KMC Systems. The normalized absorption spectra of the 2 fluorescently labeled antigens, otherwise known as chromophores or sometimes referred to as targets, are shown in the chart. The green chromophore has a center around 500 nanometers, while the red chromophore has a center around 700 nanometers. Low-cost LEDs were selected as the illumination sources. Let's focus first on the spectral convolution analysis for the green channel. The solid yellow line presents the absorption spectrum of the green chromophore, while the orange line depicts the fluorescence image for this emission for this. There are 2 items to note. One, there is an overlap of these 2 spectra in the 500 nanometer to 570 nanometer range. Second is that there is this distinct magnitude difference between the normalized absorbance spectra here and the fluorescence. These 2 items will be important for selecting various components as well as understanding what the impact of both the absorption cross-section of a chromophore is as well as the quantum efficiency. The absorption cross-section is simply this: how many photons are absorbed by a chromophore that's in a light path. And quantum efficiency is once a given chromophore absorbs a photon, what percentage of the time is that absorbed energy emitted back in observable fluorescence? As we will see shortly, both absorption cross-section and quantum efficiency can vary markedly for different chromophores. Looking at the chart, 2 additional items have been added. One, the illumination source, a green LED, depicted here. And second, an optical spectral filter or notch filter has been selected to coincide with the fluorescence while knocking out and removing crosstalk from any little bleeding through of the illumination source. At this point, we have our chromophore, which is going to absorb the energy from our LED. We have the fluorescence that's going to result from that with the associated absorption cross-section and quantum yield or quantum efficiency that we mentioned earlier. And then we have the notch filter. What remains is the impact of the actual detector. And the detector in our instance is a full color CCD, and that CCD has a sensitivity or responsivity that is variable on the wavelength. One can plot this sensitivity, as depicted here by this gray line, and we can see that it is relatively strong in terms of its sensitivity in the 500 nanometer range, but as we get to longer wavelengths in the red, it drops off. So by adding the quantum efficiency of the detector, we can see that the resultant fluorescence that we observe here by the solid green area is slightly smaller than the actual fluorescence being the yellow, the solid green being the detectable fluorescence, and that's a result of the less than 100% perfect quantum efficiency of the detector. So now what I'd like to do is clean up the green channel, and let's take a closer look at the red channel in the same basic analysis. We start with the absorption spectrum just like we did before, except now it's in the green, and once again it's centered around 700 nanometers. We then take a quick look at what the fluorescence profile looks like, and we see a couple things. One is There is considerable overlap here between about 700 nanometers and 770, not unlike what we saw with the green, but it's significantly smaller in magnitude, and there's two reasons for this. One is the absorption cross-section of this dye, or this chromophore, is significantly lower than it was for the green. And two, the quantum efficiency or quantum yield of this chromophore is also smaller, so we get hit on two of those fronts, and the end result is the resulting fluorescence from this red chromophore is substantially lower than it was for the green chromophore. An appropriately selected red LED has been chosen to overlap with the appropriate region of the absorption spectrum, but it's also been chosen so that it doesn't bleed into our emission area, and we've chosen a notch filter here depicted by the dashed cyan line so that we can collect as much of the fluorescence as possible without having crosstalk. We're also going to do the same thing we did before, which is we're going to superimpose quantum efficiency of detector, and we're going to see what impact that has on the resultant signal in our red. Now, there's a significant departure from what we see in the idealized version of what the fluorescent signal should be and what's actually measured as a result of the quantum efficiency of that detector. We're now looking at the full ensemble of signals that needed to be convoluted to understand the ramifications of the difference in the fluorescence and the various other componentry that we've spoken about. The net impact is that we see our green signal is substantially larger than our red signal here in the gray, and that's going to have ramifications for how we design our system. So let's clear up some of the extraneous signals and just take a look at the impact on what we'd actually observed through our detector. A comparison of the area of the green channel and the red channel will indicate that there is about an 8-fold difference in the magnitude of the signal. And this will have ramifications for the ability to effectively quantify the signal resulting from the red channel. Design needed to be changed as a result of this analysis, and what was effectively done was additional red LED illuminators were added to the design to bolster the signal that is seen here to a much larger value to enable effectively almost the same magnitude of signal between the green and the red channels. Another key aspect of this analysis is that it enabled an in-depth look at how manufacturing variabilities also impacted overall system design. What we've got here is basically our centralized green LED along with its associated fluorescence signal, and the centralized red LED with its associated fluorescence signal. We wanted to understand what variations in central wavelength had on the magnitude of our signal. So for example, the central wavelength is 485 nanometers for the green channel, and as we shift that to the left to more and more green, we can see that there is a net reduction in our fluorescence. Likewise, if we shift it more to the red, there's an increase. However, we also get a significantly larger amount of crosstalk, which needed to be understood and addressed. When we do the same thing for the red channel, we see as we go farther to the red, likewise we get an increase in the overall value of our fluorescence. But once again, we get creepage from the crosstalk from that. And if we move it to the left, the signal goes down, but the crosstalk reduced substantially. And while these were spectrally based analysis, we had done similar analysis to this for things such as illumination uniformity and other critical optical aspects to enable us to refine the design and to generate prototypes suitable for human clinical trials.